Hello everyone, I'm Hidri Tepe from Virginia Tech. Today I'll present DTG-Restore, a training-free diffusion refinement framework for generative video super resolution. This is a collaboration between Virginia Tech and Adobe, supervised by Pinar Yenarda and Jinrong Xie. Our key contribution is decoupled time guidance, or DTG, a simple modification to the diffusion sampling process that decouples conditional and unconditional denoising in time. This preserves geometric integrity, suppresses warp structures, and works as a plug-and-play module on top of any pre-trained video diffusion model. The motivation for this work comes from a fundamental limitation in how diffusion-based models handle restoration. Video diffusion models have achieved remarkable generative quality, but when applied to restoration or super resolution, they tend to replicate distorted evidence from the input rather than reconstructing underlying structure. In degraded or AI-generated footage, this manifests as warped geometry, stretched motion, and temporally inconsistent details. The root cause is the strong coupling between conditional and unconditional branches in standard classifier-free guidance. Both branches are evaluated at the same diffusion time step, forcing the model to stay overly faithful to corrupted inputs. Existing approaches like V-enhancer, SeedVR, and STAR either require extensive fine-tuning of large backbones or remain tied to specific training configurations. Here is the core of our method, decoupled time step guidance. The top diagram shows the intuition at each diffusion step at time t. Standard CFG evaluates both the conditional and unconditional denoiser at the same time step. We decouple them. The unconditional branch is evaluated at a cleaner time step at t minus delta, while the conditional branch stays at the current time step t. This temporal offset provides a look-ahead prior. The unconditional branch sees a cleaner version of the data closer to the data manifold, which provides the geometric structure. Meanwhile, the conditional branch at the denoiser time step guides detail and appearance. The key scheduling insight. Delta starts large in early diffusion steps for strong structure correction, then anneals to 0 in later steps for detail refinement. We use an exponential schedule. Our method preserves the underlying scene geometry without reinforcing the distortions. We reconstruct plausible high-frequency details while avoiding propagation of visible artifacts. Here are additional qualitative results across diverse real-world and generated scenes. In A, B, we show DTG-Restore applied to real-world videos, a bird on a branch and a yellow bird in a cage. The originals have motion blur and compression artifacts. DTG-Restore recovers clean, stable details with faithful color and texture. In C, a driving scene with a significant blur and distortion is corrected while maintaining temporal coherence. In D, we demonstrate the plug-and-play capability to enable proper evaluation of generative video restoration. We introduce GenWarp 480, a curated benchmark of AI-generated videos with characteristic distortions. The dataset contains 4,400 clips at 480p resolution generated from 8 different text-to-video models. It spans 550 diverse prompts across 6 major categories. Our quantitative experiments validate DTG restores across multiple evaluation axes. On standard VSR benchmarks, we remain competitive with reconstruction sampling methods like Real VFormer and MGLD VSR. Our method prioritized perceptual realism or pixel fidelity, which is the right trade-off for generative content. To summarize, we presented DTG-Restore, a training-free framework for generative video super resolution.